Alright, so now that we've introduced gas laws, the first gas law we're going to talk about is Boyle's Law. Robert Boyle, who lived from 1627 to 1691, was an Irish chemist, and he discovered that the volume of a given amount of gas that stays at a constant temperature varies inversely with the pressure. So, as pressure increases, volume decreases. And there's the demonstration of Boyle's Law there. Pressure 1 and volume 1 is equal to pressure 2 and volume 2. Okay, and here's a demonstration. Okay, as pressure increases, volume decreases. And also the other way around, as volume decreases, pressure increases. Alright, so let's solve the following. We have 825 torr. We're going to convert that to kilopascals. So remember, 760 torr was 101.3 kilopascals. So we know that 101.3 kilopascals divided by 760 torr is equal to X amount of kilopascals divided by 825 torr. And that tells us that 825 torr is 109.96 kilopascals. Okay, let's solve the other one. The volume of oxygen at 120 kilopascals is 3.2 liters. What is the volume of oxygen at 101.3 kilopascals? So again, pressure 1 times volume 1 equals pressure 2 times volume 2. And so 120 times 3.2 is equal to 101.3 times V2. And we just do some simple algebra to figure out that the volume at the end, volume at 101.3 kilopascals is 3.79 liters. This is all due to Boyle's Law. Remember, the change in pressure will be reflected in the volume in an inverse relationship. Then we also have Jacques Charles, who invented Charles' Law. He lived from 1746 to 1823 and was a French physicist. He discovered that the volume of a gas varies directly with its absolute temperature. As temperature increases, volume increases. So the formula for Charles' Law, volume 1 over temperature 1 is equal to volume 2 over temperature 2. So we're going to solve using Charles' Law. Volume of a gas of 40 degrees Celsius is 4.5 liters. Find the volume of a gas at 80 degrees Celsius. So we have volume 1 over temperature 1, 4.5 over 40. And that's going to be equal to 80 over X. Okay, but remember we have to convert Celsius to Kelvin. Okay, so 313 Kelvin and 353 Kelvin are our final temperatures, and now we can plug them in to find that 9 liters is the volume at 80 degrees Celsius or 353 Kelvin. Gay-Lussac's Law. Joseph Gay-Lussac. The pressure of a given mass of gas varies directly with the Kelvin temperature when the volume remains constant. So pressure 1 over temperature 1 equals pressure 2 over temperature 2. Remember, temperature has to be in Kelvin. So the pressure of a gas in a tank is 3.2 atmospheres at 22 degrees Celsius. If that temperature rises to 60 degrees Celsius, what will be the pressure in the tank? Remember, we must first convert to Kelvin. So 22 degrees plus 273 tells us that our T1 is 295 Kelvin. T2, 60 plus 273 is going to be 333 Kelvin. So I put 3.2 over 295, and that's going to equal X amount of atmospheres over 333. When I do my algebra, I come up with 300 3.61 atmospheres for the pressure at 60 degrees Celsius. Okay, moving on. The combined gas law. This is where Boyle's, Charles, and Gay-Lussac's laws can be combined into one single law. And that combined gas law states that the relationship among pressure, volume, and temperature of a fixed amount of gas exists. Again, remember that your temperature has to be in Kelvin. Pressure 1 times volume 1 divided by the temperature is equal to pressure 2 times volume 2 divided by the temperature. This is combining all these gas laws together. So if I want to solve this problem, a gas at 110 kilopascals is 30 degrees Celsius fills a flexible container with an initial volume of 2 liters. If the temperature is raised to 80 degrees Celsius and the pressure increased to 440 kilopascals, what's the new volume? Remember, we first have to convert 30 degrees and 80 degrees to Kelvin, so I add 273, and that's going to give me 303 Kelvin and 353 Kelvin. So pressure 1, which is 110 kilopascals, times volume 1, 2 liters, divided by 303 Kelvin, is going to equal 404 kilopascals. That's my pressure 2. We don't know our second volume, but we're going to plug a V2 in for that and divide by 353 Kelvin. Solve for V2 using some algebra, and I come up with an answer of 0.582 liters for my final volume. The ideal gas law, and this is Coach Scott's favorite. Okay, I love this gas law. This is one of the easiest ones to use. In all the other gas laws, the relationships hold true for a fixed mass or a given amount of gas sample. Because pressure, volume, temperature, and the number of moles present are all interrelated, one equation is used to describe their relationship. And again, this is the ideal gas law. PV equals nRT. P being pressure, V volume must be in liters, N is the number of moles, R is the ideal gas law constant, which we'll go over, and T, the temperature, must be in Kelvin. So the value of R depends on the pressure unit given. If the pressure unit is millimeters of mercury or torr, R is 62.4 liters times millimeter of mercury or torr over moles times Kelvin. If it's pressure, okay, that is ATM, R will equal 0.821 liters times atmospheres over moles times Kelvin. And if pressure is kilopascals, it will be 8.31. You will need to memorize these constants for R in order to use the ideal gas law. So solve the following. 44.01 grams of CO2 occupies a certain volume at STP. That's standard temperature and pressure. Find that volume. Remember that M is the sample mass of 44.01 grams divided by the molar mass of CO2. 12 plus 32. So 12 plus 32 is 44. Okay. So we have a 44.01 sample divided by a 44. If we round it up, it would be 0.01 sample. We have 1 mole of CO2. That is N. So 1 atmosphere, that was our pressure. We're looking for our volume, V, is 1 mole, N, times R. So we were dealing with STP, standard temperature and pressure. That's 1 atmosphere, so the R was 0.0821, and standard temperature in Kelvin is 273. So we know that when we multiply 1 times 0.0821 times 273, it gives me 22.4 liters. Okay, 22.4 liters. 1 atmosphere is going to equal 22.4 liters of a substance. Okay, so if I have 1 mole of something at 1 atmosphere and standard temperature and pressure, it's going to always be 22.4 liters. So solve the following. Find the molar mass of a gas that weighs 0.7155 grams and occupies a volume of 250 milliliters at STP. STP, standard temperature and pressure. So 1 atmosphere times 0.250 liters. That was our volume. We need to know moles. Okay, the molar mass will come from N. So we're searching for N. And so I have, because I'm using STP, I use R as 0.0821 again and 273 Kelvin. When I solve for that, I find that N is 0.011 moles. Okay. And 0.11 moles is equal to 0.755 grams. So I need to know the molar mass. So I put an X underneath that and I solve for X. And figure out that X is 68.64 grams per mole. That's the molar mass. Okay. So again, I solved for N, and then I plugged in into the equation that I used to solve N to begin with. So I plug in N equals the sample mass, which was 0.755 grams, divided by the molar mass, which was X, and then I solved for X. Okay, so this is the end of the gas laws. If you need to go back and review any of those, the video will be posted. Okay, it will stay here on YouTube. It's very simple. I know it seems like a lot, but once you get these down and you practice them, you will find them very, very easy. Remember, you will always need to memorize the the 3 R substitutions for the ideal gas law for each pressure unit that they change or use. Those are the main. That's a main topic from the ideal gas law, and obviously Boyle's law, Charles' law, the Gay-Lussac law, and the combined gas law are very, very important as well.